Welcome back. In this section, we're going to talk again about the difference between two means of two populations, but this time we're not talking matched pairs, we're talking independent samples. So the setup is we have some population, and we're going to take a random sample from that population, and let's say the size of the random sample is little n sub 1. And the reason I emphasize little n is that we typically use capital N for the population size. This is the sample size, not the population size. So in math and statistics, capital letters and small letters mean different things. So some people like to just change all the small letters into capital letters, but that doesn't really work in math. Okay, so anyway, so we've got this population. We're taking a sample from it. Now the population has some unknown mean. We're going to call that mean, how about we call it mu sub 1, and unknown standard deviation sigma sub 1. Well, we've got another population too. We've got a second population. We're going to take and we want to compare the means of the two populations. So we're going to take a random sample from that population. Now it doesn't have to be the same size as the other one, so we're going to use a different symbol for that. We're going to call that one n sub 2. This second population also has an unknown mean that may be different from the mean of the first population. That's actually what we want to know, is what's the comparison between mu1 and mu2. And then there will be some unknown standard deviation that we're going to call sigma 2. And again, we're interested in comparing the means of the two populations. So the types of hypothesis tests that we would do, we might do a left-tailed test, in which case the null hypothesis, the null hypothesis will always be that the means are equal. So that's your null hypothesis will always have an equal sign in it because it's assuming no difference between values. Okay, and for a left-tailed test, that's going to be if we're testing that mu1 is less than mu2. Now we really need a single number when we're working with our tables and stuff and our formulas. So I'm just going to remind you that even though what I'm thinking about is I want to know whether I'm checking here whether mu1 is less than mu2, mathematically what we're checking is whether mu2 minus mu1 is less than 0. Okay, and I don't know if I need to keep drawing pictures for what the tests look like. The left-tailed test, again, we're going to have some test statistic, and with means it's always alphas, so it's always t's, the t distribution. So left-tailed test, I'm going to get some test statistic and look for the area to the left of it. Let's see, we also have right-tailed tests. Again, the null hypothesis will be assuming no difference between the two population means, so it's always going to be the same null hypothesis. The alternate hypothesis for a right-tailed test is that mu1 is greater than mu2. Now mathematically what we're actually checking is whether mu1 minus mu2 is greater than 0. So using mu1 minus mu2, or actually using our point estimate for mu1 minus mu2, we use that to get a test statistic. That'll be a t, and we're going to look up the area to the right of t to get our p-value. And then the last type of test that we might perform is the two-tailed test. Again, H0 is the hypothesis where you assume there's no difference. The alternate hypothesis in this case is simply that mu1 is not equal to mu2. So mathematically we're checking that mu1 minus mu2 is not equal to 0. And then what we're looking for on the table, the t distribution table, okay, which is centered at 0 and symmetric about 0, we're going to look for our test statistic without a minus sign, get the area to the right of it. Look for our test statistic with a minus sign, get area to the left of that, and the sum of those two areas will be our p-value. The way we're going to do this actually is simply recognize that when the table gives me this area that's to the right, I can double that area to get the total area here because this area is the same as that area. Here is the actual test statistic. It's a t again, and I should probably use the same notation as the book. It uses t naught. Let's see. So S1 and S2 we said were the sample standard actually, I guess we didn't say that. So let's say that here. S1 and S2 are the sample standard deviations. I think what we said a little higher on the page, we just mentioned that sigma 1 and sigma 2 are the population standard deviations for population 1 and population 2. The S's refer to the samples. Similarly, we had said that mu1 and mu2 were the population means. X1 bar and X2 bar are the sample means for the sample from population 1 and the sample from population 2. So I'll just make a note of that here so we know what all the letters in the formula mean. Are sample means. And I'm going to just assume that you guys will remember that X1 bar means the mean of the sample from population 1. X2 bar means the mean of the sample from population 2. So the subscripts tell you which population you're dealing with. Now, we need degrees of freedom for the t-distribution. And in the past, we've always said that the degrees of freedom would be one less than the sample size. But in this case, our sample sizes might be different. In the last section with the matched pairs, the sample sizes were always the same because one member of a pair, well, you know, because if you sample in pairs, you get the same, you get the idea. I'm not saying that very well, but I think you get the idea. Anyway, so this time we're not sampling in pairs, so you could get a different sample size from one population than from the other. So what am I leading up to here? Well, the degrees of freedom, if there's two sample sizes, it's going to be the smaller of n1 minus 1 and n2 minus 2. So whichever, the degrees of freedom you'd get from n1 versus n2, you pick the smaller of them. When can this test be used? In other words, this method where we're using this formula? Well, the samples need to be random and independent, so not matched pairs. Either both populations have to be normal or the sample sizes have to be fairly big, so bigger than 30. In other words, N1 and N2 are both bigger than 30. And the sample sizes are no more than 5% of the respective population sizes. In other words, little n1 is less than or equal to 0.05 times capital N1. Remember, the capital letter refers to the population. The small letter tends to refer to the sample. And we also need N2 to be less than or equal to 0.05 times capital N2. So less than or equal to 5% of the size of population 2. We're also going to set up confidence intervals, so why don't we just get all the formulas here in one place, and then I'll do examples of both for you. So as usual, we have our point estimate minus a margin of error and our point estimate plus a margin of error. So the difference in the sample means is the point estimate for the difference in the population means. The margin of error, t sub alpha over 2 times the square root, and this time what's under the square root is S1 squared over N1 plus S2 squared over N2. So you'll see some similarities between the formulas in the last section where we were dealing with difference of population means, but with matched pairs, this stuff was a little simpler because we only had one standard deviation and one sample size. Okay, but that's okay, we can deal with this. Okay, so that's all the intro stuff and formulas. We'll come back in the next video and do an example. So I'll see you then.